High-speed rail metallurgy, the material science of Japan and China's infrastructure. The evolution of high-speed rail networks across the globe has consistently been defined by an invisible but violent battle against the fundamental limits of kinetic energy and material science. As the global transportation sector rapidly approaches the operational deployment of the next generation of high-speed prototypes, most notably China's CR450 and Japan's Alpha X, both slated for service integration in the coming years, the engineering paradigms governing the wheel-rail interface have been forced to undergo a radical, atomic-level transformation. To the casual observer, a high-speed train is a marvel of aerodynamic styling and electrical propulsion. However, to the metallurgical engineer, the true marvel lies in the two ribbons of steel beneath the train, which must somehow survive physical forces that by all natural laws should tear them apart. The fundamental challenge lies in the unforgiving mathematics of kinetic energy, expressed by the classic physics equation where kinetic energy equals 1/2 the mass multiplied by the velocity squared. Because kinetic energy increases exponentially with the square of the velocity, the leap from a conventional high-speed standard of 300 km per hour to the 400 and 450 km per hour targets of these new prototypes results in a massive, disproportionate increase in the destructive energy that must be safely managed by the track infrastructure. China's CR450 high-speed prototype, representing the absolute vanguard of the Flaking series, has already achieved a staggering test speed of 453 km per hour, establishing a new benchmark in global rail technology. Designed for a sustained operational service speed of 400 km per hour by 2026, the train has been meticulously engineered to minimize its physical footprint on the tracks. The CR450 is approximately 55 tons lighter and 20 centimeters shorter than its predecessors, while still maintaining an axle load of 14.5 tons. Its aerodynamic profile, featuring an extended nose cone that is 2.5 meters longer than earlier models, dramatically reduces air drag and the dangerous pressure waves generated when entering tunnels. Similarly, Japan's East Japan Railway Company, JR East, has developed the Class E956 Alpha X, an acronym for Advanced Labs for Frontline Activity in Rail Experimentation. This 10-car experimental bullet train operates as a rolling laboratory, routinely pushing its testing speeds to 400 km per hour to validate the structural and aerodynamic technologies required for a future operational speed of 360 km per hour on the extended Hokkaido Shinkansen line to Sapporo. To manage these speeds, the Alpha X is equipped with a staggering 22-meter aerodynamic nose on its Aomori-bound end, ultra-lightweight materials, and advanced emergency deceleration systems, including aerodynamic air brakes on the roof and magnetic eddy current plates near the rails. However, while aerodynamic innovations successfully mitigate air resistance, the most violent physical interactions do not occur in the air. They occur at the microscopic contact patch where the steel wheel meets the steel rail. At speeds exceeding 400 km per hour, this wheel-rail interface ceases to be a simple mechanical bearing surface and transforms into a high-energy thermodynamic reactor. If conventional untreated carbon track steel were subjected to the kinetic energy of the CR450 or the Alpha X, the metal would literally disintegrate. This disintegration does not imply that the steel turns to dust, but rather that the immense shear forces and high contact stresses lead to the rapid detachment of granular fragments, the fatigue fracture of microscopic sintering necks within the metal, and the rapid delamination of the rail surface. Furthermore, at these extreme velocities, the dynamic amplification factors push the vibration frequencies of the passing train closer to the Rayleigh wave speed of the underlying soil and track bed subgrade. This creates a resonance effect that exponentially increases the stress placed upon the crystalline architecture of the steel, leading to catastrophic track failure if the metallurgy is not specifically engineered to absorb and dissipate this kinetic onslaught. The physics of rolling contact fatigue. To understand precisely why conventional steel fails so catastrophically under the kinetic load of the CR450 and Alpha X, it is necessary to examine the highly localized physics of the wheel-rail contact patch. A high-speed train may weigh hundreds of tons, but that entire mass is transferred to the earth through an elliptical contact area on each wheel that is scarcely larger than a coin. As the steel wheel rolls along the steel rail at over 100 meters per second, it introduces an incredibly complex tensor of multi-axial stresses into the head of the rail. This stress is not merely downward vertical compression. It includes longitudinal shear stresses caused by the massive traction motors accelerating the train and the friction brakes slowing it down, as well as violent transverse shear stresses caused by the natural sinusoidal side-to-side hunting motion of the train's bogies as they seek the center of the track. This continuous high-frequency cyclic loading leads to a phenomenon known as rolling contact fatigue, which is the primary degradation mechanism threatening modern high-speed rail networks. Rolling contact fatigue manifests as microscopic cracks that initiate either precisely at the surface of the rail or just a few millimeters below it, in the subsurface zone where the maximum shear stress is concentrated. Every time a wheel passes over the rail, the metal in this localized zone is plastically deformed, pushed forward, and then released. Over millions of cycles, the ductility of the conventional steel becomes entirely exhausted. The microscopic cracks begin to propagate, often growing at a shallow angle before branching downward into the bulk material of the railhead. Once these cracks intersect, they cause large, jagged pieces of the railhead to detach completely, a dangerous phenomenon known as spalling or shelling. A track suffering from severe shelling resembles a road full of potholes, creating a rough, violently vibrating surface that further damages the wheels of the train and exponentially increases the risk of a high-speed derailment. Another severe manifestation of rolling contact fatigue is the formation of squats, which are localized, dark depressions in the center of the railhead. Squats result from the subsurface cracking and yielding of the steel, combined with the extreme plastic flow of the surface metal, creating a divot that physically hammers every passing train. Conventional steel, lacking the highly refined internal structure required to resist this constant multi-axial shearing, will rapidly succumb to rolling contact fatigue when exposed to the 400 km/h operating environments of the new prototypes. Microscopic heat zones and real-time property alteration. The mechanical stress of rolling contact fatigue is only half of the equation. The other half is governed by extreme tribological heating. At the incredible velocities achieved by the CR450 and Alpha X, the interface between the wheel and the rail is rarely a perfect rolling motion. There is always a tiny fraction of microslip, a sliding friction that occurs within the contact patch. At 400 km/h, this sliding friction generates an astonishing amount of thermal energy. It creates microscopic heat zones on the absolute surface of the rail, where the temperature can instantaneously spike to between 700 and 1000 degrees Celsius, and in extreme cases of wheel slip or heavy braking, temperatures can temporarily reach to 1400 degrees Celsius. These transient thermal spikes are incredibly brief, often lasting only fractions of a millisecond as the wheel passes over a specific point, meaning the intense heat only penetrates the top few dozen micrometers of the rail steel. However, the impact of this microscopic inferno on the material's properties is profound, and the alteration happens in real time. When the surface temperature of the steel exceeds its austenitization threshold, known as the phase transformation temperature, the crystalline structure of the steel in that microscopic zone is completely obliterated. the metal rapidly shifts from its standard body-centered cubic lattice structure into a face-centered cubic lattice known as austenite. As the train wheel continues its high-speed rotation and rolls past the contact point, the heat source is instantly removed. The massive, cold bulk of the underlying steel rail acts as a highly efficient heat sink, aggressively pulling the heat away from the microscopic surface zone. This causes the newly formed austenite at the surface to undergo an extreme, self-quenching cooling cycle. Because the cooling rate is incredibly rapid, far faster than any industrial quenching process, the carbon atoms that were dissolved within the high-temperature austenite do not have the necessary time to diffuse out of the crystalline lattice. Instead, the atomic lattice physically shears and collapses around the trapped carbon atoms, violently distorting itself into a highly stressed, needle-like structure known as Martensite. This friction-induced Martensite transformation results in the creation of a deadly surface anomaly known to metallurgists as a white etching layer. The layer earns its name from its featureless, brilliant white appearance when viewed under an optical microscope after the steel has been etched with a nitric acid solution. Its ultra-fine, nanocrystalline martensitic structure strongly resists standard chemical etching. The white etching layer is typically only 10 to 30 micrometers thick, though under intense kinetic loads it can penetrate up to 300 micrometers deep. The defining characteristic of the white etching layer is its extreme hardness, routinely measuring up to 1200 on the Vickers hardness scale, making it significantly harder than the surrounding bulk rail steel. While a harder surface might intuitively seem beneficial for resisting wear, the white etching layer is an absolute structural liability. The rapid, diffusionless transformation leaves the layer entirely devoid of ductility and introduces highly deleterious residual tensile stresses. It behaves much like a thin, highly stressed layer of glass fused directly to the top of the steel rail. Under the continuous high-frequency impacts and immense contact pressures of subsequent high-speed train wheels, this brittle, martensitic layer fractures almost immediately. Microcracks initiate either within the white etching layer itself or at the steep mechanical and structural boundary separating the hard layer from the softer, more ductile steel beneath it. These newly formed cracks serve as the primary nucleation sites for severe rolling contact fatigue, rapidly accelerating the disintegration of the rail surface and acting as the direct precursor to the dangerous formation of squats and spalls. In essence, the sheer kinetic energy of a high-speed train literally alters the metallurgical state of the track in real time, weaponizing the steel against its own structural integrity. Catastrophic failures of early high-speed experiments. To truly appreciate the metallurgical triumphs enabling the seamless operation of the 2026 CR450 and Alpha X prototypes, one must starkly contrast their performance with the catastrophic track failures that plagued early high-speed railway experiments. The history of pushing steel wheels on steel rails beyond the 300 km/h threshold is fraught with mechanical violence, serving as a series of harsh lessons where the inherent physical limitations of conventional track metallurgy were exposed with terrifying clarity. One of the most revealing early demonstrations of high-speed friction and kinetic energy overload occurred in France in the spring of 1955. The French National Railway Company, SNCF, embarked on a highly publicized, deeply ambitious effort to break the world rail speed record using two specially modified, highly powered electric locomotives, the CC7107 and the BB9004. On March 29, 1955, the BB9004 achieved a staggering speed of 331 km/h on a remarkably straight stretch of track located in the Landes Forest in southwestern France. While the record was celebrated globally as a triumph of modern engineering, the immediate aftermath of the run provided a grim reality check for the railway engineers involved. As the locomotive's driver notched down the controller to reduce power after passing the official timing trap, the immense kinetic energy, combined with aerodynamic instability and extreme frictional heating, resulted in a violent lateral oscillation known as bogie hunting. The sheer lateral and vertical forces transmitted through the wheel flanges exerted such unimaginable stress on the conventional steel rails that they physically deformed, warped, and twisted out of alignment over a continuous length of 500 meters. The track was effectively destroyed in a matter of seconds, rendering it completely impassable. Furthermore, the immense electrical draw, reaching 4,000 amperes, and the extreme aerodynamic friction completely melted the locomotive's rear pantograph, showering the roof of the train with molten metal. This 1955 experiment conclusively proved that while a train could theoretically be supplied with enough raw horsepower to reach 330 kilometers per hour, the underlying steel infrastructure was fundamentally incapable of surviving the journey. This exact engineering limitation haunted the Japanese national railways during the early formative decades of the legendary Shinkansen network. The origins of the bullet train date back to the Dangon Russia project of 1939, an aborted wartime attempt to build a wide-gauge, high-speed rail network to replace Japan's traditional narrow-gauge lines. When the Tokaido Shinkansen finally opened in October 1964, operating at the then unprecedented 210 kilometers per hour, it represented a massive paradigm shift in global transportation. However, behind the public perception of clockwork punctuality and futuristic design, the initial decades of operation were characterized by a silent, agonizing maintenance crisis. The conventional carbon steel rails used in the 1960s and 1970s suffered from rapid, unpredictable wear, severe surface corrugation, and an alarming rate of internal crack initiation. The high frequency of train passages, combined with the continuous, unyielding impact of the electric multiple unit bogies, caused the rail surfaces to rapidly develop deep shelling and transverse fissures. This material failure necessitated a massive, incredibly costly, and continuous rail replacement program throughout the late 1960s and early 1970s just to prevent catastrophic derailments. The steel of that era simply lacked the refined interlamellar spacing and the precise metallurgical purity required to endure the specific high-cycle fatigue of bullet train operations, proving unequivocally that high-speed rail is as much an exercise in advanced material science as it is in aerodynamics. The absolute physical limit of traditional rail infrastructure was perhaps most dramatically and publicly illustrated by France's Operation V150 in 2007. Seeking to establish an unbreakable ultimate speed record to showcase French engineering dominance, SNCF and Alstom heavily modified a TGV train set. They equipped it with extra-large wheels to cover more distance per rotation and a heavily boosted 25,000 horsepower distributed traction system. On April 3, 2007, the TGV V150 reached an astonishing, earth-shattering speed of 574.8 kilometers per hour. However, this incredible feat was an absolute stress test of the physical environment, pushing both the machine and the track to the brink of disaster. Reporters aboard the train during the record run noted that at 380 kilometers per hour, the vibrations from the track became highly pronounced. By 590 kilometers per hour, passengers began to feel physically dizzy from the high-frequency lateral oscillations transmitted through the floor. At 540 kilometers per hour, the kinetic energy transfer between the wheels and the rails was so violent that it was nearly impossible to remain standing in the carriages. The track used for the record, a newly constructed segment of the LGV East Line, required highly specialized preparation, and the overhead catenary voltage had to be temporarily increased from standard 25,000 volts to an immense 31,000 volts just to overcome the immense aerodynamic drag and mechanical friction. The V150 record unequivocally proved that pushing steel wheels on steel rails beyond 500 kilometers per hour brings the entire system to the very edge of physical disintegration, generating thermal and mechanical stresses that would rapidly destroy any standard rail network in regular commercial service. Even at significantly lower speeds, the failure to actively manage material stress, rolling contact fatigue, and vibration has led to tragic consequences. The 1998 Eschede train disaster in Germany, which claimed 101 lives, serves as a dark, unforgettable reminder of the consequences of high-speed metal fatigue. While the failure at Eschede initiated in the steel tire of a dual-block wheel design rather than the track itself, the root cause, unmanaged rolling contact fatigue and microcracking propagating silently through a critical load-bearing steel component, is the exact same physical mechanism that threatens high-speed rails. The sudden explosive destruction of the wheel tire caused the train to derail and violently strike a bridge pier at 200 km/h, demonstrating that in the realm of high-speed kinetic energy, a microscopic metallurgical flaw can rapidly scale up into a macroscopic catastrophe. The silent, flawless performance of modern Japanese and Chinese alloys, contrasting sharply with the violent instability, rapid degradation, and constant maintenance emergencies of early high-speed rail experiments, the modern track networks supporting the 2026 CR450 and Alpha X prototypes are engineered to operate with an eerily silent flawlessness. This perfection is not the result of magically altering the laws of physics, but rather the culmination of decades of obsessive, incremental refinement in metallurgical engineering. Modern high-speed rails do not merely passively endure the passage of a train, they are highly engineered, responsive composite structures at the microscopic level, designed specifically to actively dissipate energy, resist frictional wear, and prevent the nucleation of fatigue cracks. China's approach to supporting the incredible 400 km/h operational speeds of the CR450 relies heavily on the deployment of advanced alloyed rail steels, most notably the highly engineered U75V and U78CRV grades. Standard rail steel, such as the older U71MN grade, contains primarily carbon, 0.68% to 0.78%, and manganese, and focuses entirely on providing basic mechanical strength for conventional freight and passenger lines. However, the extreme contact pressures and immense shear forces generated by the CR450 demand a material capable of resisting intense plastic deformation while maintaining absolute surface integrity. The Chinese U75V grade achieves this by aggressively increasing the carbon content to a hyper-eutectoid level of 0.72% to 0.82%, and crucially, adding between 0.04% and 0.12% vanadium to the alloy mix. Vanadium is a remarkably potent microalloying element. When it combines with carbon during the cooling of the steel, it precipitates as incredibly hard nanoscale vanadium carbide particles that distribute themselves evenly throughout the crystalline matrix. These microscopic precipitates act as physical roadblocks, restricting the movement of dislocations within the crystal lattice, which dramatically refines the grain size of the steel. This nanoscale reinforcement exponentially increases both the wear resistance and the deep fatigue life of the rail, allowing it to shrug off the kinetic impacts that would destroy standard steel. For even more demanding track segments, such as sharp curves or high-stress acceleration zones where wheel slip is common, Chinese metallurgists deploy the premium U78CRV grade. This high-end alloy maintains the high carbon and vanadium content, but introduces 0.30% to 0.60% chromium into the melt. The addition of chromium serves to significantly depress the temperature at which the steel transforms during its cooling phase, allowing for the natural formation of a much finer, denser crystalline structure without the need for excessively rapid, potentially brittle quenching. The unique synergy of chromium and vanadium in the U78CRV rail results in a material that demonstrates an exceptional combination of high tensile strength and ductile elongation, definitively preventing the surface matrix disintegration that plagues standard steels under 400 km/h kinetic loads. Japan's strategy for outfitting the ALFX infrastructure focuses on absolute hyperpurity and the utilization of deep head-hardened paralytic rails, specifically variants like the JISE E60 grade. Nippon Steel and other Japanese rail manufacturers have continuously optimized their smelting and casting processes to produce rails with almost zero non-metallic inclusions, the microscopic impurities like alumina or complex silicates that naturally occur in steelmaking. Because these hard, brittle inclusions serve as the exact stress concentrators where rolling contact fatigue cracks nucleate, effectively eliminating them through incredibly clean steel practices ensures that the risk of internal crack initiation is almost entirely neutralized. Furthermore, the highly prized silent performance of these modern networks is achieved through a holistic, systemic approach to acoustic and vibrational damping. High-speed rail noise is not primarily aerodynamic. It is generated by the microscopic irregularities on the wheel and rail surfaces interacting at incredibly high velocities, vibrating the track like a guitar string. To combat this, modern networks exclusively utilize continuous welded rails, or CWR, ribbons of steel that are hundreds of kilometers long, completely eliminating the expansion joints that caused the rhythmic, damaging clatter of legacy railways. In addition to removing joints, the rails are often fitted with specialized rail dampers, heavy polymer and steel composites that are bolted or glued directly to the vertical web of the rail. These dampers act as acoustic shock absorbers. They capture the high-frequency vibratory energy generated by the ALFX and CR450 and convert it into low-grade heat through internal friction within the rubber matrix. This drastically reduces airborne noise and prevents the vibration from propagating down the track into the surrounding environment. The trains themselves, such as the CR450, employ fully enclosed bogies and multi-stage independent cushioning systems, which work in perfect harmony with the advanced rail alloys to create a seamless, whisper-quiet glide path even at 450 kilometers per hour. The crystalline architecture of rails, Pearlite and Martensite. To truly comprehend why these modern alloys succeed so spectacularly where conventional steels fail, one must look deeper than the chemical composition and examine the crystalline architecture of the steel at the nanometer scale. The mechanical properties of a railway track are not solely dictated by the raw elements melted into the furnace, but by the precise geometric arrangement of its iron and carbon atoms as the metal cools, its microstructure. In the realm of high-speed rail metallurgy, the dominant microstructures of intense interest are Pearlite and Martensite, and the physical interplay between them entirely defines the survival or failure of the track. It might seem highly intuitive to the layperson that to withstand the immense wear, friction, and impact of a train traveling at 400 kilometers per hour, the rails should simply be made of the hardest possible material available. Martensite, named in honor of the pioneering German metallurgist Adolf Martens, is exceptionally, fiercely hard. As previously detailed regarding the white etching layer, Martensite is formed when austenite is cooled or quenched so rapidly that the carbon atoms simply do not have the time required to diffuse out of the crystalline lattice. This violent thermodynamic event traps the carbon atoms in a highly stressed, distorted, body-centered tetragonal structure. While Martensite provides immense surface hardness and virtually unparalleled wear resistance, this rapid diffusionless transformation results in extreme internal tensile stresses, a massive dislocation density, and a near-total lack of ductility. A railway track made entirely of bulk Martensite would be incredibly, dangerously brittle. Under the immense bending stresses of the train's weight, the lateral hunting of the bogies, and the dynamic vertical impacts of high-speed travel, a fully martensitic rail would simply shatter like tempered glass. Therefore, while microscopic zones of friction-induced martensite are an unavoidable tribological consequence on the absolute surface of the rail, bulk martensite is entirely unsuitable for the primary load-bearing architecture of a high-speed rail network. Instead of brittle martensite, the engineering backbone of the Shinkansen and the Chinese high-speed networks relies on a fully paralytic microstructure. Pearlite is a naturally occurring two-phase nanocomposite that forms when steel is allowed to cool at a controlled, moderate rate, allowing carbon diffusion to occur. It consists of alternating microscopic layers, or lamellae, of two completely distinct phases. Ferrite, scientifically known as alpha iron, is a relatively soft, highly ductile phase with a body-centered cubic structure that contains almost zero dissolved carbon. Cementite, which is iron carbide, is an extremely hard, rigid, and brittle ceramic-like compound. When a cross-section of this steel is polished, etched, and viewed under an electron microscope, these alternating layers strongly resemble the iridescent striated surface of mother pearl, giving the microstructure its distinctive name. The absolute genius of the paralytic architecture lies in this material duality. The hard cementite lamellae act as microscopic armor plates, providing exceptional resistance to abrasive wear and preventing the railhead from being ground down by the relentless passage of steel wheels. Simultaneously, the soft ferrite layers act as an internal microscopic shock-absorbing matrix, granting the bulk steel the essential ductility and flexibility required to bend elastically under the massive weight of the train without snapping. The ultimate physical performance of a paralytic rail is almost entirely governed by a single critical metric, the interlamellar spacing, denoted in metallurgical literature as SP. This is the physical distance between the parallel layers of hard cementite. According to the metallurgical principles defined by the Hall-Petch relationship, as the interlamellar spacing decreases, both the yield strength and the overall hardness of the pearlite increase exponentially. This strengthening occurs because the closely packed cementite layers act as impenetrable physical barriers to the movement of dislocations, the microscopic slip planes that allow metal to bend within the soft ferrite matrix. The closer the layers are packed together, the harder it is for the metal to deform plastically. In standard low-speed rails, the interlamellar spacing might be relatively wide, perhaps around 300 nanometers. However, the advanced alloys used for the CR450 and Alpha X infrastructure, such as the heavily refined R350 HT grade, are engineered through precise thermal control to achieve an incredibly fine, tightly packed interlamellar spacing of between 77 and 115 nanometers. At this extreme nanoscale resolution, the hardening coefficient reaches its absolute peak. This provides a rail that is highly resistant to both abrasive wear and the initiation of rolling contact fatigue, all while maintaining the vital flexible core necessary to prevent a catastrophic brittle fracture. Vacuum degassing and the hidden killer, hydrogen flaking. Even with the perfect chemical composition and an optimized pearlitic microstructure, a newly forged high-speed rail can harbor a microscopic hidden killer that is entirely invisible to the naked eye, yet completely capable of causing sudden, catastrophic track failure. Hydrogen gas. The phenomenon of hydrogen embrittlement has historically been one of the most insidious, unpredictable threats to railway safety, leading to internal material defects known in metallurgy as shatter cracks, fish eyes, or hydrogen flakes. During the primary steelmaking process, the molten iron is inevitably exposed to various sources of moisture, including atmospheric humidity, damp raw charge materials, alloy additions, and even the refractory brick linings of the furnaces. At the extreme temperatures of a steel furnace, exceeding 1500 degrees Celsius, this water vapor disassociates, and the resulting highly active atomic hydrogen readily dissolves directly into the liquid steel. In its molten liquid state, Steel possesses a high natural solubility for hydrogen, easily accommodating 5 to 12 parts per million of the gas. The physical crisis occurs during the cooling and solidification phase. As the steel transitions from a chaotic liquid to a structured solid crystalline lattice, its capacity to hold dissolved hydrogen plummets drastically to roughly 0.1 ppm. Because the hydrogen atoms can no longer be physically accommodated within the shrinking, tightening crystalline lattice, they are forcibly rejected from the solidifying matrix. These highly mobile hydrogen atoms migrate rapidly through the hot steel and accumulate at internal defects such as microvoids, grain boundaries, or non-metallic inclusions. Once gathered in these microscopic pockets, the individual hydrogen atoms chemically recombine to form molecular hydrogen gas. Because the gas is trapped within a confined, sealed space inside the rigid, cooling steel, the localized pressure builds exponentially, easily exceeding the tensile yield strength of the surrounding metal. This violent internal rupture creates a microscopic, silvery, disc-shaped internal fracture, a hydrogen flake or shatter crack. When a hydrogen flake forms within the solid head of a rail, it serves as the ultimate, perfectly placed stress concentrator. As thousands of heavy trains roll over the rail, the localized pressure at the sharp tip of the internal crack causes it to slowly propagate outward, eventually forming a massive, deep-seated transverse fissure. Because the crack grows entirely internally, the visible surface of the rail appears completely normal and safe to visual inspection until the fissure reaches a critical, fatal diameter. At that exact point, the remaining steel can no longer support the massive load of the passing train, and the entire rail snaps suddenly and violently. In the early 20th century, before the exact mechanism of hydrogen embrittlement was fully understood by metallurgists, this terrifying phenomenon caused thousands of deadly derailments. The initial rudimentary solution, developed in the 1930s, was controlled cooling, often called bloom cooling. In this process, the hot steel was placed in heavily insulated boxes and allowed to cool agonizingly slowly over several days, giving the highly mobile hydrogen atoms enough time to diffuse entirely out of the steel before it could form damaging gas molecules. However, for the ultra-high performance alloys required by the CR450 and Alpha X, controlled cooling is not only insufficient to guarantee absolute purity, but it also severely limits production throughput in modern steel mills. Therefore, modern high-speed rail steel undergoes a highly sophisticated secondary metallurgical process known as vacuum degassing. After the steel is melted and refined in the primary furnace, the ladle of liquid iron is transferred into a hermetically sealed vacuum chamber. High-capacity liquid ring vacuum pumps evacuate the atmosphere above the molten steel, creating a near-perfect vacuum. According to Sievert's law, the solubility of a diatomic gas in a metal is directly proportional to the square root of the partial pressure of that gas above the melt. By drastically lowering the atmospheric pressure in the chamber to near zero, the thermodynamic equilibrium is violently shifted. The dissolved hydrogen, nitrogen, and oxygen are literally sucked out of the liquid steel, bubbling violently to the surface where they are extracted by the pumps. Furthermore, vacuum degassing offers a secondary, highly critical metallurgical benefit: vacuum carbon deoxidation. In the low-pressure environment, the dissolved carbon within the steel reacts directly with the dissolved oxygen to form carbon monoxide gas, which is also extracted by the vacuum system. This effectively deoxidizes the steel without requiring the addition of large amounts of solid deoxidizers like aluminum or silicon. When used in open air, these solid deoxidizers leave behind hard, brittle oxide inclusions, like alumina, that act as prime nucleation sites for rolling contact fatigue. The vacuum degassing process efficiently and reliably reduces the hydrogen content in the melt to well below 1.5 parts per million, safely below the critical threshold for flake formation, resulting in a hyper-pure, incredibly tough steel bloom that is completely free of internal shatter cracks and primed to endure decades of high-speed impacts. Deep head hardening and specialized heat treatments. The final, most critical engineering hurdle in crafting a rail capable of surviving the 400 km/h operating environments of the CR450 and Alpha X is resolving the paradoxical physical requirements of the track structure itself. The very top surface of the rail head must be incredibly, exceptionally hard to resist the abrasive wear and immense contact pressures of the high-speed wheels. However, if the entire cross-section of the rail were hardened to that extreme degree, it would lose the vital elasticity required to bend, flex, and absorb the dynamic shock waves, thermal expansion, and heavy axle loads without fracturing. The elegant solution lies in creating a highly controlled metallurgical gradient through an advanced thermomechanical process known as deep head hardening. Deep head hardening is an in-line treatment immediately after the red-hot rail emerges from the final shaping rollers at the steel mill. Rather than allowing the finished steel to cool naturally in the ambient air or quenching it violently in a water bath, the rail passes continuously through a massive computerized multi-stage cooling station, which can be over 100 meters long. Here, the head of the rail is subjected to a highly precise process called slack quenching, an accelerated cooling process utilizing forced compressed air or a fine atomized air-water mist. The absolute physics of this cooling process dictate the final interlamellar spacing of the Pearlite, and thus the ultimate strength and survival of the rail. Extensive metallurgical modeling and dialometric testing have established that for high-grade pearlitic steels like the European R350HT or the Chinese U75V, the absolute optimal cooling rate lies strictly within a narrow envelope of between 3 and 6 degrees Celsius per second. To achieve this precise thermal drop, the cooling stations apply compressed air at carefully calibrated pressures, typically around 6.5 bar. If the cooling rate is too slow, falling below 3 degrees Celsius per second, the austenite transforms into coarse pearlite with a wide interlamellar spacing, resulting in a rail surface that is far too soft to withstand high-speed wear, failing to meet required hardness standards. Conversely, if the cooling rate is too aggressive, exceeding 6 to 8 degrees Celsius per second, the steel crosses a dangerous critical thermodynamic threshold, resulting in the accidental formation of undesirable bainitic structures or completely brittle, fracture-prone martensite. By maintaining the cooling rate perfectly within the 3 to 6 degrees Celsius per second envelope, the accelerated cooling forces the austenite to transform into ultra-fine pearlite at a much lower temperature than it naturally would. This creates a surface layer with an extremely tight interlamellar distance of approximately 80 nanometers, yielding a surface hardness that easily exceeds 350 to 400 Brinell hardness number. The absolute brilliance of the deep head hardening process is its targeted geometry. The accelerated cooling jets are directed exclusively at the top and upper gauge sides of the railhead, the areas that will directly contact the train wheels. Because thermal energy conducts relatively slowly through the bulk mass of solid steel, the cooling rate naturally diminishes as one measures deeper into the cross-section of the rail. While the surface cools at nearly 4 degrees Celsius per second to form ultra-hard pearlite, the interior of the railhead cools at a slower, more relaxed rate of approximately 2.6 degrees Celsius per second. This slower internal cooling results in a slightly wider interlamellar spacing, around 110 nanometers, and a slightly lower hardness. This precise thermal management creates a seamless, continuous gradient of strength rather than a sharp boundary line between hard and soft steel. A sharp transition would create a dangerous shear plane, a distinct zone of mechanical weakness where subsurface rolling contact fatigue cracks could easily initiate due to the mismatch in material stiffness. Instead, the deep-head hardened rail features a highly wear-resistant, ultra-hard crown that gradually and naturally yields to a softer, highly ductile core in the web and base of the rail, which typically registers a much more flexible 280 bhn. This tough, flexible core acts as the true structural spine of the track, absorbing the immense bending moments, the high-frequency lateral impacts, and the thermal expansion stresses of the environment, while preventing the hardened surface layer from cracking under impact. By mastering the cooling curve of steel, engineers have created a rail that is simultaneously armor-plated against friction and flexible enough to carry the future of human transport. The successful impending deployment of the 450 km/h CR450 and the 400 km/h Alpha X prototypes is not merely a superficial triumph of aerodynamic styling, nor is it simply a victory of brute force electric traction power. It is fundamentally and unequivocally a victory of atomic architecture. The kinetic energy generated by these incredible machines is immense enough to instantly deform, melt, or disintegrate conventional infrastructure, as proven by the disastrous high-speed experiments of the 20th century. However, by deeply understanding the thermodynamic realities of the wheel-rail interface, metallurgical engineers have effectively neutralized the high-speed friction crisis. Through the meticulous nanoscale refinement of pearlitic interlamellar spacing, the absolute eradication of hydrogen flaking via vacuum degassing, and the precise orchestration of strength gradients through deep head hardening, modern rail networks have transformed basic steel into a dynamic, highly resilient composite. This material is uniquely capable of silently managing the most extreme commercial transportation environments on Earth, ensuring that as humanity pushes the boundaries of speed, the ground beneath our feet remains unbroken. End of the Click-Clack, understanding thermal expansion and seamless stability. For more than a century, the sensory experience of traveling by train was defined by a rhythmic, unmistakable sound, the steady click-clack of steel wheels rolling over the tracks. This sound, deeply embedded in the cultural consciousness of the industrial age, was not a deliberate design choice, but rather an engineering compromise forced by the unforgiving laws of thermodynamics. Early railway systems were constructed using the short rail method, a system characterized by discrete, manageable segments of steel laid end-to-end and joined together using mechanical bolts and overlapping metal fish plates. These mechanical joints were absolutely critical because they provided strategic physical gaps between the rails, allowing the steel to naturally expand during the searing heat of summer and contract during the freezing depths of winter. However, this mechanical concession to temperature variations introduced severe systemic vulnerabilities to the global railway infrastructure. The presence of thousands of joints along a rail line created relentless mechanical discontinuities. Every time a heavy train wheel crossed a gap, it generated a violent impact stress, hammering the ends of the rail segments and sending shock waves through the rolling stock. Over time, these impacts caused rapid degradation of the train wheels and the track infrastructure itself, while simultaneously subjecting passengers to severe vibrational discomfort. More importantly, these joints acted as a fundamental speed limit on human travel, as moving too fast over segmented tracks would literally shake a train apart. The technological imperative to eliminate these joints and unlock higher speeds became a driving force in civil engineering, culminating in a massive, coordinated technical effort during and immediately following the Second World War. The result of this global metallurgical pursuit was the advent of long welded rails, commonly referred to within the industry as continuous welded rail infrastructure. By developing advanced welding techniques to fuse individual track segments into an unbroken, continuous ribbon of steel, sometimes stretching for hundreds of kilometers without a single break, engineers successfully eradicated the mechanical joint, paving the way for the smooth, silent glide of the modern high-speed rail era. However, the transition from jointed tracks to a continuous molecular strand of steel did not rewrite the laws of physics. Materials still expand when heated and shrink when cooled. Without expansion joints to accommodate the physical lengthening and shortening of the steel, the massive thermal energy absorbed by the tracks is no longer expressed as movement. Instead, it is converted directly into immense trapped internal mechanical stress. The physics governing this phenomenon are rooted in the concept of restrained thermal expansion. Just as all physical materials exhibit a predominantly linear relationship between thermal fluctuations and dimensional expansion, they also possess a corresponding relationship between applied mechanical stress and the resulting change in length, a property commonly referred to as strain. The engineering secret to the seamless stability of continuous welded rail infrastructure is that the natural tendency of the steel to expand or contract is physically counteracted and overpowered by the sheer holding force of the track system itself. By securely clamping the rail to heavy sleepers and by deeply embedding those sleepers within a heavily compacted rock ballast or a rigid poured concrete track bed, the track structure artificially restricts the movement of the central portion of the continuous rail. In a properly secured long welded rail, physical movement is only permitted at the absolute terminal ends of the track segment, while the vast majority of the steel is held in a state of rigid, highly stressed immobility. The magnitude of the forces generated within this trapped steel is staggering, and calculating them forms the bedrock of modern track safety. The thermal force generated within a rail is determined by a strict mathematical formula. It is the product of the modulus of elasticity of the rail steel, the coefficient of linear expansion, the cross-sectional area of the rail, and the total variation in temperature. To put this into perspective, for standard high-strength rail steel, the modulus of elasticity stands at an immense 2.15 million kilograms per square centimeter, and the coefficient of linear expansion is precisely 1.152 multiplied by 10 to the power of -5 per degree Celsius. When a continuous rail undergoes a significant temperature shift, the resulting thermal force must be entirely and flawlessly resisted by the track components. Because the rail is trapped, a sudden drop in temperature induces profound internal tensile stress. The cold steel attempts to shrink but is held fast, effectively stretching the metal at a molecular level and raising the terrifying risk of spontaneous, explosive, brittle fracture. Conversely, a sharp rise in temperature induces massive compressive stress. The hot steel attempts to lengthen but cannot, threatening to violently buckle the track laterally in a catastrophic failure known to engineers as a sun kink. To manage this delicate and highly dangerous balance, track engineers employ a highly calculated physical process known as de-stressing. The objective of de-stressing is to lock the rail into its heavy-duty fastenings at a highly specific target temperature, establishing a neutral zero-stress state at a strategic midpoint between the historical maximum and minimum temperatures of the specific geographic region. This process can be achieved naturally by temporarily unfastening the rail and allowing it to freely expand and contract until the ambient air temperature perfectly matches the calculated neutral temperature, or artificially by utilizing heavy-duty hydraulic rail tensors. These massive hydraulic machines grab the ends of the rail and apply a mathematically precise mechanical extension, literally stretching the cold steel to the exact length it would be on a warm day, before workers permanently lock it down into the fastenings. The complexity of thermal stress management is further amplified when long welded rails are laid across monumental engineering structures, such as the massive vibrating suspension bridges required to carry high-speed rail networks over wide rivers and deep valleys. The spatial finite element modeling of bridge-track interactions demonstrates that the thermal forces exerted on the rail are deeply interconnected with the swaying and structural movements of the bridge itself. To ensure driving safety and passenger comfort on these suspended superstructures, engineers must utilize specific correction methods to maintain the rail in a zero-stress state immediately upon laying. On massive main-span suspension bridges, such as those exceeding 1,000 meters in length, specialized rail expansion joints must still be strategically utilized, but they are vastly more sophisticated than the crude gaps of the past. These advanced joints must be laid at a calculated distance away from the primary beam end, preferentially selecting bridge beams with substantial integral stiffness to anchor them. Dynamic and static structural analyses indicate that under extreme expansion loads, these specialized bridge joints can safely accommodate sliding displacements exceeding 380 millimeters. They act as complex mechanical shock absorbers, handling a superimposed load of multi-axial forces generated not just from temperature swings, but from the physical braking of the train, the bending of the bridge, and even seismic earthquake activity. Forging the unbreakable molecular strand, the metallurgy of thermite welding. Transforming discrete, heavy segments of steel into a continuous, unbroken molecular strand capable of carrying thousands of tons of train load day after day relies on one of the most violent, spectacular, and highly precise chemical reactions utilized in modern civil engineering, the aluminothermic welding process. Commonly referred to in the field as thermite welding, this fusion process is a triumph of applied high-temperature chemistry. It relies on a rapid exothermic reduction-oxidation reaction between refined aluminum powder and iron oxide to generate the extreme localized heat required to completely melt high-carbon rail steel right on the tracks. The fundamental principle driving this chemical inferno is that aluminum acts as a highly aggressive reducing agent. When ignited, the aluminum violently strips the oxygen atoms away from the iron oxide in a self-sustaining chain reaction. This rapid exchange of molecular bonds releases a blinding amount of thermal energy, instantly producing a pool of pure liquid molten steel and a lighter byproduct of liquid aluminum oxide slag. Executing a flawless thermite weld on an active high-speed rail line is not merely a matter of lighting a chemical fire. It is a process that demands absolute surgical precision to ensure the metallurgical integrity of the resulting joint. The operation begins with the meticulous preparation of the two rail ends that are to be joined. Workers must ensure the heavy steel beams are perfectly aligned and completely free of physical damage, microscopic cracks, or structural distortion. Using wire brushes and grinding wheels, the steel is polished to a high shine, removing any trace of rust, moisture, oil, or surface deposits that could contaminate the weld. The track engineers then carefully adjust the physical size of the gap between the rails to a highly specific tolerance, typically holding strictly between 26 and 30 millimeters. A precise amount of vertical camber is also established, slightly elevating the rail ends by exactly 1.5 to 2 millimeters. This slight elevation is a calculated necessity, deliberately introduced to account for the natural, unavoidable shrinkage of the molten steel pool as it solidifies and pulls the rails together during the cooling phase. Once the geometry is perfect, a specialized refractory mold is clamped securely around the gap, creating a sealed, heat-resistant cavity that mirrors the exact physical profile of the rail. Prior to igniting the thermite charge, the rail ends enclosed within this mold must be subjected to intense, prolonged preheating using a high-pressure torch. This preheating is essential to stabilize the steel and prevent the incoming 2,500-degree liquid metal from instantly chilling and violently fracturing upon contact with the cold rail. Once the optimal preheat temperature is achieved, the exothermic reaction is initiated within a dedicated, reusable or single-use crucible, positioned directly above the mold. In a matter of seconds, the violent chemistry converts the dry powder into a blindingly bright, churning pool of liquid metal. The crucible is then mechanically tapped, and the molten steel is discharged directly into the refractory mold, flawlessly filling the precise gap between the rails, while the lighter aluminum oxide slag floats to the top and is safely discharged into specialized overflow bowls positioned on the sides of the track. While the macroscopic process of pouring the metal appears straightforward and highly industrial, the true engineering miracle occurs completely out of sight at the microscopic level during the critical cooling phase. As the molten weld pool rapidly solidifies, its internal crystalline grain structure begins to take shape, and this invisible microstructural phase entirely dictates whether the weld will last for a few months or for decades of heavy use. The thermodynamic cooling rate is the master variable in this metallurgical equation. If the weld is allowed to cool too rapidly, the carbon atoms trapped within the iron lattice are denied the time they need to migrate, forcing the steel to form martensite. Martensite is a highly strained, ultra-hard, and dangerously brittle microstructural phase that is exceptionally susceptible to sudden catastrophic fatigue cracking under the relentless impact of train wheels. Conversely, if the weld cools too slowly, the resulting crystalline grains have too much time to grow, becoming excessively large and leaving the joint structurally weak, soft, and prone to physical deformation. The ultimate target of the controlled cooling process is the formation of a fine, tightly packed paralytic structure, perfectly mirroring the metallurgical composition found in the premium rail steels themselves. Achieving this specific crystalline lattice guarantees that the weld possesses the exact balance of shear strength, flexibility, ductility, and fatigue resistance necessary to withstand millions of cycles of heavy axle loading without shattering. To meet the highly diverse load requirements of modern global rail networks, metallurgists have developed distinctly different chemical formulations of the thermite charge. When joining premium, high-strength rail segments, such as head-hardened rails designed for heavy freight, or those heavily alloyed with chromium, molybdenum, and vanadium for high-speed use, engineers must utilize highly specialized alloy thermite charges rather than standard mixes. The chemical composition of these alloy mixes incorporates critical microscopic additives and chemical reductants, including calcium silicide, silicides of barium or strontium, and specific rare earth metals like yttrium and cerium. These precise microscopic additions serve as powerful deoxidants within the molten pool. More importantly, they function to physically spheridize non-metallic inclusions within the liquid steel, essentially rounding off the sharp edges of any microscopic impurities. By preventing the formation of sharp, jagged internal flaws, these additives eliminate the primary nucleation sites where microscopic fatigue cracks typically begin to grow. The resulting alloy weld metal exhibits substantially higher hardness values, ranging from 268 to 314 on the Brinell hardness scale, and boasts tensile strengths 15 to 20 kilopounds per square inch greater than standard thermite mixes. However, the laws of metallurgy demand a trade-off. This increased strength comes at the cost of reduced tensile ductility, with the alloy welds exhibiting lower impact energies of merely 1.5 to 2.8 joules at ambient temperatures. The intense thermal gradients generated during this violent welding process fundamentally alter the structural state of the surrounding unmelted rail steel, creating a highly sensitive physical region known as the heat-affected zone. Within this zone, the steel undergoes a complete and chaotic spectrum of metallurgical transformations. At the boundary closest to the molten pool, the extreme heat induces the formation of transitional pearlite and localized bainite structures. At the furthest outer edge of the zone, the steel experiences a localized tempering effect, leading to the spheridization of the pearlite and creating a dangerous, narrow region of minimum material hardness. Furthermore, the rapid shrinkage of the solidifying metal introduces massive residual stresses into the track structure itself. The outer regions of the weld, which naturally cool and solidify first, contract rapidly, placing themselves under immense residual tensile stress as they pull tightly against the rest of the rail. Simultaneously, the inner core of the weld, which remains hot and expands against the shrinking outer shell, is forced into a state of intense compressive stress. To mitigate these highly complex mechanical variables, the fully cooled weld is rigorously ground back to the exact geometric profile of the original running surface. This meticulous grinding ensures that the heavy train wheels pass over the newly fused molecular joint with absolute glass-like smoothness, completely free of any microscopic impact or load concentration. Only after passing rigorous visual inspections, hardness evaluations, and ultrasonic non-destructive testing, searching for hidden voids deep within the metal, is the brief burst of high-temperature chemistry officially certified as a permanent, continuous piece of high-speed track. Managing the massive internal stresses of the Chinese hinterlands. The aggressive expansion of China's high-speed rail network into the deepest, most remote reaches of the Asian hinterlands represents an unprecedented planetary-scale challenge in the field of material science. The sheer geographic vastness of the network exposes the infrastructure to a brutal, unforgiving spectrum of extreme operational environments, demanding rail and structural materials capable of enduring conditions that would rapidly destroy traditional steel and aluminum alloys. The Harbin-Dalian high-speed rail line serves as a prime example of this engineering gauntlet. Stretching for 928 kilometers through the seasonal frozen soil regions of China's northeast, the rails in this region are subjected to an environment where the annual temperature differential can easily exceed a staggering 70 degrees Celsius. Under these severe climatic conditions, the massive repeated freeze-thaw cycles of the surrounding Earth, combined with the extreme thermal expansion and contraction of the steel rails themselves, subject the entire track and subgrade system to relentless long-term dynamic loading that threatens to tear the infrastructure apart. To fully grasp the structural mechanics of these colossal thermal swings, researchers have conducted extensive experimental and numerical stress analyses on the specialized China Railway Track System Type 2 ballastless track structures, which utilize massive continuous concrete slabs instead of traditional crushed rock. Finite element modeling of scaled structural specimens subjected to extreme thermal loading has revealed that the physical strains distributed throughout this system are deeply interconnected. As the temperature fluctuates, strain builds non-linearly throughout the concrete track slab, the specialized cement emulsified asphalt mortar layer acting as a cushion, and the deep foundational track bed. The computational data demonstrates a profound thermodynamic dichotomy that engineers must design around. Severe drops in ambient winter temperatures generate massive tearing tensile stresses across the different strata of the track structure as the materials desperately try to shrink. Conversely, high-temperature summer spikes induce severe relative physical displacement, threatening to shear the rail fastening systems right off the track bed and disrupting the underlying box girder bridge architecture. To survive the sheer physical punishment of the hinterlands, a metallurgical philosophy driving China's high-speed rail development heavily prioritizes extreme durability, raw mass, and wear resistance. This philosophy is distinctly evident in the chemical formulation of the 60 kg per meter U75V and U71MNG rail steels, which serve as the predominant metallic backbone of the national network. The U75V rail steel is a masterclass in high-carbon, high-strength industrial metallurgy. It is heavily alloyed with specific ratios of carbon, manganese, and silicon, but its defining characteristic is the precise inclusion of vanadium. Vanadium acts as a powerful microalloying agent, forming microscopic carbonitride precipitates that pin the grain boundaries of the steel in place, preventing them from shifting under stress. Through advanced accelerated cooling techniques during the manufacturing process, the microstructure of the U75V steel is driven into a highly refined state, achieving formidable surface hardness values. Monotonic tensile testing of this material confirms its high-strength behavioral profile, exhibiting an immense load-bearing capacity with almost negligible physical necking or elongation at the point of ultimate fracture. The long-term durability of these rails is largely dictated by the microscopic spacing of their pearlitic lamellae, the alternating microscopic layers of soft iron and hard iron carbide that make up the steel's internal structure. Extensive tribological analysis indicates that manipulating the physical distance between these microscopic layers directly influences the wear resistance and fatigue damage resilience of the steel. For the dedicated high-speed passenger lines, where trains run fast and light, a microstructure with a relatively larger lamellar spacing is often selected to specifically resist the onset of microscopic fatigue damage caused by high-frequency wheel contact. Conversely, in mixed-use lines that must accommodate both sleek passenger trains and significantly heavier freight loads, a medium lamellar spacing is preferred to provide a highly balanced, robust resistance against both raw physical grinding wear and cyclic fatigue. The behavior of these specialized steel microstructures under the continuous high-speed impact of rolling stock is fundamentally governed by the physics of fatigue crack propagation. Uniaxial tension compression fatigue characterizations of the U75V rail steel have rigorously mapped its high cycle fatigue endurance, establishing a formidable baseline fatigue strength of 515 megapascals over 5 million continuous operational cycles. However, because steel is imperfect, microscopic cracks will inevitably form over time. The growth kinetics of these microscopic fissures are highly complex. Crack propagation analysis reveals that the speed at which a fracture deepens into the rail is dictated not only by the applied stress intensity range, but also by the absolute magnitude of the loading force exerted by the train. As the maximum loading force increases, exposing the steel to heavier trains, a critical micromechanical phenomenon known as the plasticity-induced crack closure effect is triggered. Under immense dynamic stress, the metallic grains located directly ahead of the microscopic crack tip are crushed and deform plastically. When the wheel load passes and the stress is temporarily removed, this plastically deformed zone expands slightly, physically pressing against the opposing faces of the crack. This action artificially wedges the crack shut, thereby shielding the fragile crack tip from further immediate tearing and exponentially slowing the overall rate of structural failure, allowing the rail to survive the brutal conditions of the hinterlands much longer than standard steel. The optimization of the welding process for these specialized hinterland steels has required further exacting metallurgical refinement. In flash butt welded joints, a process that uses massive electrical currents to melt the rail ends together without thermite, the exact concentration of manganese plays a highly critical role in determining the ultimate toughness of the molecular fusion zone. High-speed photographic and scanning electron microscopy studies have revealed that marginally decreasing the manganese content in U71Mn steel from 1.03% to exactly 0.94% fundamentally enhances the microstructural quality of the weld. This seemingly minor reduction in the alloying element successfully suppresses the formation of brittle martensitic phases during cooling and drastically reduces the precipitation of large, soft manganese sulfide inclusions. Because these inclusions act as internal stress concentrators that nucleate fatal microcracks, their removal is vital. By optimizing the composition, engineers achieved a remarkable 65% increase in the raw impact toughness of the welded joint, while significantly minimizing the length of dangerous network ferrite formations within the web region of the rail, guaranteeing a stronger track across the frozen plains. This continuous battle against extreme hinterland environments extends far beyond the steel rails to the train bodies themselves. The high-speed electric multiple units navigating these vast routes must endure radical aerodynamic loading, high-frequency vibration, intense ultraviolet radiation, and severely corrosive industrial atmospheres alongside the extreme cold. The foundational aluminum alloys initially utilized in Chinese train manufacturing exhibited concerning vulnerabilities in these extreme wide-area environments, specifically demonstrating insufficient stability regarding their long-term fatigue behavior and a dangerous susceptibility to stress corrosion cracking. To overcome these severe material deficiencies, Chinese material scientists engineered highly advanced microalloyed variants of aluminum, culminating in the A7N01S-T5 alloy. By carefully infusing the aluminum matrix with microscopic, tightly controlled concentrations of iron, copper, chromium, zirconium, manganese, and zirconium, metallurgists radically altered the grain boundary chemistry of the metal. This advanced extrusion material boasts an ultimate strength exceeding 325 megapascals and a remarkable fatigue strength, drastically reducing its sensitivity to stress corrosion and ensuring the long-term survivability of the car bodies operating in the unforgiving extremes of the Chinese interior. Next-generation high-entropy alloys, the 2026 breakthroughs for 400 kilometers per hour. As global railway networks relentlessly continue to push the boundaries of mechanized velocity, the physical demands placed upon train components and track infrastructure are escalating past the capabilities of traditional metallurgy, entering an entirely new regime of material science. The absolute vanguard of this acceleration is the Chinese CR450 project, an engineering marvel explicitly designed to shatter existing operational benchmarks by achieving a sustained commercial passenger speed of 400 kilometers per hour. Following a highly successful series of track tests on the Cross-Sea Meizhou Bay Bridge, where the CR450 prototype achieved an astonishing, record-breaking peak single-train test speed of 453 kilometers per hour, the global rail industry has officially entered what researchers call an uncharted innovation zone. Reaching these unprecedented velocities required a total ground-up reimagining of both the exterior aerodynamic profile of the CR450, shaping it to pierce the atmosphere with minimal resistance. Engineers achieved a massive 22% reduction in high-speed aerodynamic drag, while simultaneously reducing the overall weight of the consist by 10%. However, the true revolutionary leap in performance stems from the train's transition into the permanent magnet era. The traction system of the CR450 is driven by highly advanced, domestically developed permanent magnet synchronous motors, which provide an immense improvement in raw electrical traction efficiency. The deployment of these hyper-efficient motors, however, introduced severe operational risks. Unlike traditional electromagnets that can be turned off, a permanent magnet is always on. If a short circuit occurs between the motor windings at 400 kilometers per hour, the motor will not stop spinning due to the continuous presence of the permanent magnetic field, creating a potentially catastrophic threat to high-speed operational safety as the motor tears itself apart. To neutralize this threat, researchers engineered a groundbreaking three-phase active short-circuit protection mechanism. This digital safety net is capable of detecting a microelectrical fault and redirecting the massive electrical current through a closed, safe loop in a mere 0.2 seconds, instantly preventing mechanical disintegration and ensuring passenger safety. While the electrical and aerodynamic systems have been pushed to their theoretical limits, maintaining physical, structural stability at 400 kilometers per hour imposes immense high-frequency cyclic contact stresses at the critical dime-sized interface between the speeding steel wheel and the stationary steel rail. At these extreme velocities, traditional nickel-based superalloys and conventional high-carbon rail steels begin to approach the absolute limits of their physical endurance. They simply cannot handle the heat and vibration without softening or cracking. To ensure total track and wheel stability for the operational commercial launch of the CR450 network in 2026, the material science community has turned to a revolutionary, paradigm-shifting class of advanced metallurgical composites, high-entropy alloys, HEAs. Traditional metallurgical design for the last 3,000 years has relied on a primary base element such as iron in steel or nickel in aerospace superalloys, which is then carefully enhanced with minor fractional additions of secondary alloying elements. High-entropy alloys represent a total revolutionary abandonment of this ancient paradigm. Instead of relying on a single base metal, HEAs are synthesized by mixing 5 or more principal elements in near equiatomic, massive concentrations. For the extreme temperature and mechanical stress requirements of next-generation high-speed rail, researchers have specifically focused on refractory high-entropy alloys, utilizing heavy, ultra-resilient transition metals such as titanium, niobium, hafnium, tantalum, zirconium, molybdenum, vanadium, and tungsten. The stabilizing mechanism of these hyper-complex alloys is rooted deeply in the thermodynamic laws of the universe. According to the foundational principles of physical chemistry, when multiple, vastly diverse atomic elements are mixed together in equal, massive proportions, the system generates an immense level of configurational entropy. Entropy is essentially the measure of disorder or chaos in a system. This extreme state of elemental chaos is so thermodynamically powerful that it completely overcomes the enthalpy of compound formation, which is the natural thermodynamic drive of different metals to clump together and bond into rigid, highly brittle intermetallic compounds. Instead of forming a fragile, shattered crystalline structure full of weak points, the extreme entropy forces the diverse atoms to settle into a remarkably simple, highly stable solid solution, typically adopting a face-centered cubic or body-centered cubic crystalline lattice. It's a metallurgical paradox. By maximizing the chemical chaos of the ingredients, the final structure becomes perfectly uniform. This entropic stabilization allows metallurgists to completely bypass the traditional, highly restrictive trade-off between metallic strength and physical ductility. Because the constituent atoms in a high-entropy alloy possess substantially different physical sizes and atomic radii, forcing them into a single uniform crystalline grid creates massive internal atomic distortion, much like trying to stack bowling balls, tennis balls, and marbles into a perfect pyramid. This intense lattice distortion creates massive internal friction that highly impedes the movement of microscopic dislocations through the metal. When the immense cyclic contact stresses of a train wheel rotating at 400 kilometers per hour attempt to rip the metal apart, this atomic traffic jam stops the cracks from propagating, rendering the alloy unbelievably strong. Furthermore, researchers have engineered these metastable alloys to exhibit extraordinary self-reinforcing behaviors under stress, such as transformation-induced plasticity. Under the crushing impact of high-speed rail loads, the internal crystal lattice of the HEA can instantaneously and reversibly transform its structure, instantly hardening the exact point of impact while allowing the surrounding metallic matrix to remain ductile and absorb the catastrophic shock waves without shattering. Manufacturing these highly complex multi-elemental alloys for high-speed rail applications has required the rapid adoption of cutting-edge production technologies. Traditional vacuum induction melting or arc melting processes often result in severe elemental segregation, excessive oxidation, and the formation of enormous weak crystal grains measuring up to 200 micrometers in diameter. To overcome these fatal casting flaws, engineers in 2026 have heavily industrialized the use of laser powder bed manufacturing. By utilizing high-powered lasers to instantaneously melt and fuse microscopic beds of precisely blended pre-alloyed metallic powder layer by layer, the LPBF process achieves cooling rates so unimaginably fast that the diverse elements are instantly trapped in their perfectly homogeneous solid solution before they have time to separate. This rapid laser-induced solidification forces extreme microstructural grain refinement, successfully reducing the average grain size down to a microscopic 13.4 micrometers. The resulting additive manufactured HEAs exhibit micro-hardness values that are literally double those of their conventionally cast counterparts, completely mitigating internal forming flaws and delivering compressive yield strengths well over 2 gigapascals. This absolute mastery over elemental entropy and laser fusion manufacturing is the silent metallurgical foundation that allows the 400 km/h CR450 to ride smoothly, safely, and seamlessly across the track. Diverging iron pathways, Shinkansen lightweighting versus Chinese heavy hull durability. The metallurgical and mechanical design of high-speed rail networks is not a universal, one-size-fits-all science. It is deeply and heavily dictated by the specific geographic, historical, and philosophical priorities of the nation constructing it. A comparative analysis between the pioneering Japanese Shinkansen system and the rapidly expanding Chinese high-speed network reveals a profound divergence in engineering philosophy, fundamentally altering how each nation utilizes structural alloys, distributes physical mass, and manages the inevitable long-term degradation of track infrastructure. The Japanese Tokaido Shinkansen, inaugurated in 1964 as the world's first true high-speed rail line, was born out of an intense national imperative to create a safe, high-capacity transport artery along a highly congested, geographically constrained, and severely earthquake-prone island corridor. Because the Japanese were pioneering high-speed operations entirely from scratch, without any historical precedent to rely upon, their initial engineering designs were characterized by an extreme adherence to safety margins and structural conservatism. Operating on a relatively weaker, older machinal track bed compared to the massive fortress-like concrete foundations utilized decades later in Europe or China, Japanese engineers became hyper-focused on minimizing the physical punishment inflicted upon their rails. To preserve the track infrastructure while safely operating at high speeds, Japan adopted a strict, uncompromising philosophy of extreme lightweighting and distributed traction. Rather than pulling the passenger cars with a massively heavy locomotive concentrated at the front of the train, which would generate track-crushing axle loads and rapidly destroy the rails, the Shinkansen system utilizes electric multiple units. In this configuration, nearly every single axle along the entire length of the train is independently motored. This complete distribution of propulsion equipment perfectly and evenly disperses the weight of the train, rigorously maintaining exceptionally low maximum axle loads that barely stress the steel beneath them. Furthermore, Japanese metallurgists poured immense research into developing ultra-lightweight aluminum bogies and specialized wheelbases designed to absolutely minimize the train's unsprung mass, the heavy, rigid components that sit below the suspension system and hammer directly against the steel rails. By transitioning almost entirely to regenerative electrical braking, which uses the motors to slow the train and generate electricity, the Shinkansen system was even able to eliminate the heavy, heat-generating mechanical brakes on non-motored axles, further stripping massive amounts of weight from the train undercarriage. This deep national obsession with lightweighting and environmental efficiency extends to the very life cycle of the Japanese alloys. In recent years, Japan has perfected the highly complex metallurgical process of recycling the massive amounts of aluminum utilized in retired Shinkansen car bodies. Historically, the thick layers of industrial paint, the chemical adhesives, and the deep embedding of high-strength steel bolts made it physically impossible to purify the retired aluminum for reuse in highly stressed structural applications. However, advanced chemical extraction and rigorous alloy sorting processes now allow engineers to completely strip these contaminants, recovering high-purity, aerospace-grade aluminum alloys. This closed-loop recycling process drastically reduces the immense electrical energy required to smelt new aluminum from raw bauxite ore, successfully slashing the carbon dioxide emissions associated with manufacturing a new Shinkansen train body by an astonishing 97%, saving over 50 tons of emissions per train. In stark contrast to the Japanese philosophy of delicate lightweighting and rail preservation, China's high-speed rail development began from an urgent 21st-century mandate to rapidly interconnect a massive, geographically diverse continental landmass. Beginning in the early 2000s, China strategically absorbed and adapted the world's leading high-speed technologies, including early assistance from Japan and Germany, synthesizing them into a distinctly robust, domestically driven engineering ecosystem tailored to their unique geography. The Chinese design philosophy prioritizes heavy haul durability and sheer infrastructural resilience, designed to thrust massive passenger capacities across vast distances that feature some of the most punishing topographies on the planet. Because the modern track beds and concrete subgrades are engineered from the ground up to be extraordinarily massive and rigid, their rails are fully capable of absorbing significantly higher dynamic impacts than the older Japanese lines. Consequently, Chinese engineers are not strictly bound to the absolute light-weighting constraints that define the Shinkansen. While China heavily utilizes the distributed traction electric multiple unit model, they comfortably and safely deploy highly mixed train set formations, such as setups featuring 14 heavily motored cars and 2 unmotored trailer cars. This heavier, mixed configuration deliberately sacrifices absolute weight reduction in exchange for vastly superior high-friction mechanical braking performance, an absolute physical necessity when decelerating massive, heavy-haul trains operating at 350 to 400 kilometers per hour. The metallurgical composition of the Chinese wheels, axles, and undercarriage components is heavily biased toward thick, high-strength, heavy-duty alloys designed to maximize longevity and resist the extreme vibrational fatigue of continuous cross-continental high-speed operation. It is a national strategy that confidently values brute infrastructural permanence and passenger volume over the delicate, feather-light preservation of the rail surface. Conquering coastal corrosives, rare earth elements in salt air environments. While the deep hinterlands challenge rail infrastructure with extreme thermal expansion and freezing dynamic loads, the deployment of high-speed rail networks along the expansive Chinese coastlines, such as the vital Hainan Ring Island High-Speed Railway, introduces an entirely different, highly aggressive agent of structural destruction: severe marine corrosion. The atmosphere in these tropical coastal environments is heavily saturated with extreme humidity, intense radiant heat, and a relentless, invisible microscopic mist of highly reactive airborne salt. When traditional high-carbon rail steel is exposed to this chloride-rich environment, the chloride ions act as aggressive electrochemical catalysts. They rapidly penetrate the natural microscopic oxide layers of the steel, violently accelerating the anodic dissolution of the iron matrix. Left unchecked by chemical intervention, this marine environment will induce rapid, deep pitting corrosion, hollowing out the steel from the inside, stripping the rails of their mechanical strength, and acting as immediate nucleation points for catastrophic fatigue failure. To render the rail infrastructure highly immune to this relentless electrochemical onslaught, metallurgists have turned to the strategic integration of rare earth elements, specifically cerium and lanthanum, into the molten chemistry of advanced railway steels. The protective mechanisms generated by these microscopic additions are incredibly complex, operating across multiple physical and chemical phases during the entire life cycle of the metal, from the blast furnace to the coastal tracks. The defensive process begins inside the roaring heat of the steel mill. When trace amounts of these highly reactive rare earth elements are injected into the liquid steel melt, they exhibit an immense thermodynamic affinity for oxygen and sulfur, vastly outperforming traditional industrial deoxidizers like magnesium or aluminum. The The cerium and lanthanum aggressively scavenge the liquid steel, chemically binding with highly detrimental trace impurities, including titanium, lead, arsenic, and antimony. Furthermore, the rare earth inclusions fundamentally modify the physical morphology of the non-metallic inclusions that naturally form within the steel. In standard rail steel, soft manganese sulfide inclusions are physically stretched into long, sharp, needle-like stringers during the intense physical rolling process, creating microscopic, dangerous internal fault lines. The addition of cerium completely alters this dynamic. The cerium reacts to form complex compound inclusions such as cerium aluminate and cerium oxysulfide. Because these rare earth inclusions are exceptionally hard, perfectly spherical, and highly resistant to physical deformation during the rolling process, they maintain the absolute structural continuity of the steel matrix, drastically reducing the steel's sensitivity to internal cracking. However, the true mastery of rare earth alloying is revealed when the finished rail is actually laid down and exposed to the corrosive marine atmosphere. As the steel inevitably begins to react with the humid, salty air and oxidize, the embedded rare earth atoms actively manipulate the electrochemistry of the resulting rust layer. In standard steel, the initial corrosion product is predominantly gamma FeOOH, a highly unstable, porous, and heavily flawed iron hydroxide that easily flakes away, leaving the raw, vulnerable steel constantly exposed to further chloride attacks. The presence of cerium, however, electrochemically forces the rust to rapidly transform its molecular structure into alpha FeOOH, an incredibly dense, highly stable, and electrically insulating phase of rust. This rare earth-induced alpha FeOOH layer packs so tightly against the surface of the rail that it establishes a near impenetrable physical barrier, completely shutting down the microscopic transmission pathways utilized by the corrosive chloride ions to attack the iron. First principles quantum simulations demonstrate that the cerium atoms physically segregate at the exact interface between the raw steel matrix and this dense rust layer, creating an active, polarized rare earth atomic shield. This polarized shield significantly enhances the thermodynamic adhesion work between the substrate and the rust, locking the protective oxide layer permanently to the steel and completely arresting the dynamic lateral extension of the corrosion process. The practical results of this atomic-level engineering are profoundly evident in modern coastal applications. When subjecting newly developed rare earth-infused steels, such as the advanced U68CuCr rail steel, to highly aggressive neutral salt spray tests and simulated subsea tunnel environments, electrochemical testing confirms a massive positive shift in the steel's self-corrosion potential. The heavily alloyed U68CuCr steel consistently maintains a dramatically thicker, highly protective impedance radius compared to standard high-speed rail steel, exhibiting significantly lower weight loss and ensuring that the high-speed tracks tracing the coastlines remain absolutely stable, structurally sound, and impervious to the invisible electrochemical fires of the ocean. Through the mastery of thermal expansion, high-entropy lattice distortion, and rare earth chemistry, the modern railway has truly conquered the elements, allowing humanity to travel at breathtaking speeds safely across the harshest environments on Earth.